Hello, it's Ryan again, working with another movement learning live stream section of my live streaming. That didn't come out right. But yeah, Wednesdays I'm working with mostly reviewing pen and paper physics and math, in part to reestablish my own relationship with these materials, trying to attend to myself while I go through it and not get so fixated on learning things that I actually compromise my own comfort. Um, Further adding to the difficulty, I'm doing this live on camera, reviewing or even learning new things. So all kinds of opportunities to squirm. And if you want to follow along, you're welcome to go to this website, feynmanlectures.caltech.edu, and pick up Chapter 9 and start following along with me. And there are a number of locations that this live stream is being ported to. You can find me on YouTube, Vaughn Live, or Twitch, also Facebook, although it appears that the Facebook setup for live streaming isn't, I'm not using it very interactively these days. Seems to be a little bubbled. So at any rate, you could also get my attention by actually figuring out my contact info and contacting me directly. I do have my phone here, and I can get text messages and such. So those are the things. How are you doing? Are you comfortable in your chair or wherever you're listening to this? I'm doing pretty good today. Let's get at these notes. As usual, there's a picture of what the blackboard looked like. Before this chapter, we could not calculate how a mass on a spring would move. Much less could we calculate the perturbations on the planet Uranus due to Jupiter and Saturn. But after this chapter, we will be able to compute not only the motion of the oscillating mass, but also the perturbations on the planet Uranus produced by Jupiter and Saturn. Excuse me. So Galileo discovers the principle of inertia, that an object left alone continues to move with a constant velocity in a straight line. And of course, this never appears to be the case. A block sliding on the table is slowed due to the friction, a second force, slowing the inertia, removing the inertia. But the right rule is inertia, and that's due to Galileo, not just inactive thinking, but imagination, as any good scientist will emphasize. Of course, the next thing which is needed is a rule for finding how an object changes its speed if something is affecting it. Right, because Galileo was looking at nearly frictionless things, the movement of planets around each other. Definitely apparently frictionless from the Earth viewer. But Newton describes the actual changes required. So the first law is inertia. And the second law, a specific way of determining how velocity changes under different influences called forces. F equals ma. The third law, it describes the forces to some extent, and we shall discuss that at another time. Okay, so this whole chapter is on the second law, which asserts that the motion an object is changed by forces, which asserts that the motion of an object is changed by forces in this way. The time rate of change of a quantity, called momentum, is proportional to the force. Let's explain the idea. Momentum is not the same as velocity. Goes through some distinction between mass and weight. Mass is the right measure of inertia. And so here's the definition: momentum, product of mass and velocity. So there's Newton's second law, F equals the change of the product of mass times velocity. So if the mass is constant, and additive so then you can pull the EM out of that and just write the change in velocity with time, which is the acceleration. So that's how you get F equals ma, equation 9.2. Because it's a constant times something changing. And emphasizing that change in direction counts as a change in velocity. Hmm. Hmm. I don't recall that derivation he's referring to. So just scanning. Oh, here we go. 7.4. Okay, this is the thing he's talking about. Right. So X there is is showing if there was no force keeping it in a circular path, it would continue in a straight line. And so there's some geometry here. Hmm. Yeah, this is a bit to digest. Our tangent is the mean proportional between the two parts of the diameter cut by an equal chord. Okay. So this is one part of the diameter, that's the other part of the diameter, cut by the same chord, cut by an equal chord. Where did the 16 come from? Oh, that's just G in feet. Okay, I see. Okay, didn't fully absorb that, but let's move on. So this is for circular motion, the relationship between the acceleration required to keep it on a circular path for a given radius and a given velocity. Yeah, I've never been that comfortable with this stuff, and I wish I could derive it better. That last figure, I didn't absorb completely, I'm sure. Anyway, in order to make our language more precise, we're going to distinguish speed and velocity, got directions of velocity. And just setting up some notation for the movement of an object from the, the back left corner to the front right corner of this box. Writing the x, y, and z displacements. And the overall vector, delta s. And just more notation. The change in x with respect to time is velocity in the x direction, etc. Speed is the absolute value of the velocity. Cartesian, or whatever, the length, the distance. And so then in 9.2, we're looking at a change in velocity. And the recipe is to evaluate the x, y, and z components independently. And Feynman's wording is, in these terms, we see that Newton's second law, in saying that the force is in the same direction as the acceleration, is really three laws, in the sense that the component of the force in xyz direction is equal to mass times the rate of change of the corresponding component of velocity. If an object is accelerating, some agency is at work. Find it. Our program for the future dynamics must be to find the laws for the force. In the case of gravity, he gave a formula for the force. In the case of other forces, he gave some part of the information in his third law, having to do with the equality of action and reaction. That's the next chapter. So extending the previous example, what are the forces on objects near the Earth's surface? So we have a Hooke's law spring where the force is going to be proportional to the displacement. So there's some equilibrium position for the spring, and then when you move from it, you get a force proportional to this constant. So, and the force is opposite to the direction of the displacement. Right. So it's negative kx is equal to mass times acceleration in the x direction. We're calling it x. It's vertical. Yeah. So this statement is the kind of thing that I love now, and it took me a lot of studying physics to appreciate what physicists are doing when they make constants go away like this. But so you can happen to have a mass that makes it so that k over m equals a natural number 1. And yeah, it simplifies it greatly. I didn't actually follow that's a simple piece of arithmetic I can try to work out live. Um, I should really try to do this with that figure, that plane geometry thing I didn't understand. But you have negative kx is equal to the mass of the thing times dx by dt. Is that right? Yeah. So then, yeah, let's say that do you say k over m or m over k? K over m, I suppose. K over m equals 1. Then k is equal to m. I see. And then so it's negative m x is equal to m acceleration in the x direction. So whatever the position is, it's accelerating in the opposite direction by x units if you've worked out with this. Huh. The thing about the units though is very confusing because this is going to be in something like meters, and this is going to be in something like meters per second squared. So, hairy, some subtle things happening here. But the acceleration is negative x. Yeah, there you go. So we're trying to analyze what this equation means. The acceleration is negative x. Suppose that at a given time, it's got a velocity and a position. What is the velocity? What is the position after an increment? just describing a small change in the position due to a small time increase, epsilon. I'm just saying that the distance is a function of time. Okay, just following this along. So the velocity in the next time increment is equal to the initial velocity plus the time increment times the acceleration, which is itself a function of time. And this is the kind of thing I never would have worked through before, and I really should have. So I'm going to take some time with this numerical solution of these equations. Let us really solve the problem. take a small epsilon of 1/10 of a second. Maybe we need to make it even smaller. And so we had an initial value of 1 for the x position. So at time 0, it's 1 x unit up. And so from the simplification of the force law, we know that its acceleration is -1. So in the first instant, it's got 0 velocity, and it adds a negative velocity of 0.1 units to it. So then we can update the position in the next tiny little fragment of time. It's where it was in the previous fragment, which is still at its starting location to this approximation. And then another increment of movement. Right, because that's the velocity, so it's velocity times time gives us the increment of movement. Okay, so that gives us the position and the new velocity. So the easy way to make this precise is to make epsilon very small, but then it takes many more computations to calculate the same thing, or calculate the apparent movement over the same time. So we're going to make a subtle improvement in the technique of the analysis. The new position is the old position plus the time interval epsilon times the velocity. But the velocity when? The velocity at the beginning of the time interval is one velocity, the velocity at the end of the time interval is another velocity. So the improvement is to use the midpoint velocity. And so the approximation is to use the intermediate speed that's changing over that interval. So the improved approximation uses the equations. The updated position is the previous position plus the time of that interval times the velocity halfway through the trajectory, halfway through that interval. And that, the velocity halfway through the interval, I don't completely grok the second one. Some simple averaging thing, I think. So like before at initial time 0, it's at its initial position, x equals 1. And it's starting at rest. And there's the second value that's put underneath the velocity to represent that epsilon over 2 point at 0.05 between 0.0 and 0.1. So it's written underneath the 0. And you get a negative 0.05. So that value is the initial velocity plus half of right. So just like any kinematic equation, the velocity is being updated with an acceleration. And yeah, we knew the initial acceleration that was also given from right. Okay. Hmm. It's pretty interesting. This ends up being a cosine function. We're numerically calculating a cosine function from this simple harmonic motion. There's a trick there, the special equation for getting this started. Just drops it in. But then, yeah, the idea is that if you update the next the next x position based on the midpoint velocity, you get a better calculation, more accurate. Okay, so Feynman thinks this is very nice for an oscillating spring, but what about the motion of a planet? Can we get the elliptical orbit? All right, time to work in 2 dimensions. So we're going to approximate the sun as infinitely massive or fixed. It's not moving, and the planet's being pulled towards it. We're going to assume that z is always 0 because there's no force in the z direction. And if there's no initial z velocity, there's nothing to make z other than 0. Doing a 2-dimensional treatment here. The wording here isn't how I'd word it, so I'm going to try to actually follow it. Horizontal component of the force is related to the complete force in the same manner as the horizontal distance x is to the complete hypotenuse r, because the 2 triangles are similar. Yeah, okay. And getting the sign set up correctly, that the force is in the opposite direction of x here. So the magnitude of that force is given by Newton's law. There's a little bit of stuff here I'm going to try to actually wrap my head around properly, because often when I see Newton's law in vector form, Newton's law of gravitation in vector form, I get confused by the r cubed in the denominator because it's an inverse square law. But it's all about vectors and directions, because there's also a direction going into the numerator here, the x. So in a unit-wise, from a unit perspective, you're dividing by a square of distance in the denominator. Similar considerations for the y direction. We've got these three equations. To make the numerical work easier, we're setting big G and the mass of the sun equal to 1. The initial position of the planet is x.5 and y is 0. And the velocity in the y direction, okay, we're assuming this. That it initially has y velocity and not x velocity is strange to me. I don't completely get it. Because we're starting. Yeah, no, I don't completely get that. And so yeah, this is the generalization of it. And the explanation for how it can be made arbitrarily precise by making epsilon smaller and smaller. So continuing through chapter 10, conservation momentum. If all the forces are internal, there's no external forces, then the total momentum is constant. This is the third law. So on the basis of the second law, F equals ma, any problem in mechanics can be solved in principle. It reminds me when Peter Wallace said, all you need to know is F equals ma to do molecular dynamics, which I didn't feel was exactly right, but technically right, theoretically right. Um, so yeah, we've learned a general recipe for numerical analysis. Talking about analytical solutions. In the situations in which we cannot follow details, we need to know some general properties, some theorems, general theorems or principles, which are consequences of Newton's laws. One of these is conservation of energy, another is conservation of momentum. Action equals reaction. Conservation of the total momentum of a number of interacting particles is a constant if there are no external forces. The laws of physics will look the same whether we are standing still or moving with a uniform speed. Galilean Relativity. Before discussing collisions in which two bodies collide and stick together, or come together and bounce apart, we shall first consider two bodies that are held together by a spring or something else, and are then suddenly released and pushed by the spring or perhaps by a little explosion. So in one dimension first, the two objects are symmetrical, and then there's a little burst, a little explosion between them, so that one body is moving to the right. It appears reasonable that the other body is moving towards the left with the same velocity, because the objects are identical, and so we probably do something symmetrical. So now let's pick different densities for the object, but keep the masses the same. Okay, so you kept doing the experiment with things at different densities. You could find the situation where they respond to that explosion by producing the same velocities, and then they would have the same masses. If two masses are equal to a third mass, are each equal to a third mass, then they're equal to each other. The statement does not follow at all from a similar statement used as a postulate regarding mathematical quantity. I don't completely absorb this. It seems subtle. It's not just a definition to say the masses are equal and the velocities are equal. Because to say the masses are equal is to imply the mathematical laws of equality, which in turn, okay, yeah. In the development that follows, we shall assume it is true that equal masses have equal and opposite velocities when an explosion occurs between them. For the inverse case of two identical objects moving in opposite directions with equal velocities collide and stick together, they'll come to rest after the collision. And conservation of momentum, playing with air troughs. First, that if two stationary objects of equal mass are separated by an explosion, they will move apart with the same speed. And if two objects of equal mass coming together with the same speed collide and stick, they will stop. So you can work with the air trough, which eliminates much friction. That's a fun experiment. So you explode them apart, they rebound off the ends and come together and stick. So it works, and third law is real. Let's do a less simple situation. Excuse me. Two equal masses, one with velocity v and the other standing still, and they collide and stick. What is going to happen? Right. So it forms a mass of 2m, but what is the velocity then? So working with Galilean relativity. Hmm. So this discussion is looking at a collision from two different frames of reference. And from both frames of reference, the momentum is the same, although the apparent velocities afterwards are different. Before and after are different. So two equal bodies of these velocities, they collide and stick together. this way of thinking through it is definitely losing me. Why we need to work with relative motion constantly here? It's a little bit beyond me. Yeah, I'm getting cooked. I think I'm gonna call it for the day. Uh, so trying to make sense of momentum using all these air trough experiments, following Feynman's actual train of thought. A little sleepy. So yeah, that's it for today. In tomorrow's time slot, I will work with the movement organizing theme, which is the most interesting from the perspective of those that are students of somatic education or teachers of somatic education. Um, Probably continuing with the theme from, well, the line of thinking from last week on the information processing paradigm for looking at the living condition and what this has to do with biological functions. So tune in, same time, 10 a.m. till noon Mountain Time. So that's starting at 9 a.m. On Pacific Time and noon on the East Coast, Eastern Time of Turtle Island. Thanks much.